Brilliant, I think we're live. Hello everyone, thanks for joining us today and welcome to today's pizza session on spatial data science. I'm very happy to be here today with Philippa Wood, a spatial data scientist here at PA Consulting, and as usual we'll be leading off with a quick interview to sort of set the scene and get a bit of a feel for both what led Philippa here and the topic itself. Before that though, for those of you who haven't attended one of these sessions before, I want to give a little bit about who we are and what we do. So the pizza sessions are a series of live streams and events that run every 4 to 6 weeks, where data scientists from our team here at PA Consulting give in-depth seminars on different areas of expertise. These are deeply technical and hopefully really interesting too. The leading principle behind all of this is that data science has always thrived on active, inclusive communities, and we want to do our part to build one with this series. So join our meetup network and check out the YouTube channel at Real Data Science, where you can see our previous sessions, they're all recorded, and also add comments and let us know what you would like us to cover in the future. So now, I think housekeeping's out of the way, onto the fun stuff. Thanks for being here today, Philippa. Excited to hear about spatial data science. We're really looking forward to getting into the meat of the presentation and demo and seminar almost. But before that, you need to make it through a quick interrogation from me.
Okay, let's go.
So first up, hopefully the easy one. Why do we need spatial data science in today's world?
Basically, we're working in a real world, with real world problems. So if you only do analytics that don't reflect that locational dimension, then you're missing out on that real insight that you're going to give your clients or customers, that information that reacts to where in the world those requirements, recommendations are needed. And to make sure that's done cohesively, recognizing that are geospatial data principles that must be adhered to. So yeah, basically we live in the real world, so we need real world tools to help us get there.
Fantastic. I think that's really nicely put. It's that sort of real world elements that we're able to bring with spatial data science that takes it beyond maybe what people historically think of when they think of geospatial data. To that point, the second question sort of digs into that. What I wanted to ask you next is, over the last 10 years and your time working in this field, how has it changed in your eyes? Or have you seen it change?
Yeah, definitely. I feel that there has been a real step change in spatial data industry. It typically used to be GIS professionals that were trained in specific tools, working at very detailed level and creating some very good plots, cartography principles and rules. But now, actually what's happening is geospatial is no longer a niche. It's actually blended completely with other technologies, and obviously computer science and the power of programming and the data science that goes with that is like the perfect mix to really unlock that power. The other main thing has been the technical change in computational power. We're working with complex real-world systems, and there's always had to be that compromise that a model is a representation, but we don't actually need to make such big generalized situations, because we can actually do digital twinning, we can do real-time analytics on highways. All of this is possible because we've now got the computing power to mix with the spatial and those data science technologies. So this is just creating this kind of amazing opportunities to really deliver the real complex solutions and insights, and especially the depth of deep learning that you can get from the data science tools we now have available. So of course you want to put it all together and see what we can do to inform, and especially in consultancy, help our clients deliver very insightful answers.
Yeah, that makes perfect sense. I think that especially that one around the computational power, what we're able to work with these days, you sort of find people develop things to work within the constraints that are placed upon them. You're pragmatic. You think, how can I solve this problem? But I might only have this much power to use. Then when the power opens up to you, you don't want to lean on those same tools that were built under constraints, but find ways to evolve them. And that sounds like the way spatial data science is going and why it's exciting right now.
Absolutely, because we can make the here and now, and there's, just bring it all to life.
Fantastic. So, final question before we get on to the good stuff. Today, as part of your presentation, you're going to be talking about Cilla. Can you give us a brief summary of what Cilla is and how it's also evolved over time?
Yeah, actually, Cilla is strategic investment location analysis. It's all about providing a key framework for multi-criteria problems when you've got lots and lots of parameters, how you can use data science effectively with the power of location. How it's come about is, firstly, this was part of my academic journey and part of postgraduate research that created this framework. The presentation case study I'm going to use today was actually that thesis case study that was from those times. But this has actually been an idea that has followed me through my academic journey. So in a previous master's, I was working on renewable energy siting, and this was back in the days 10 years ago when we didn't really have that data science integration. So you're very much limited to weighted map algebras, just layering on things with a bit of math in there. And everything's weighted and subjective. I'll get into that in more detail, but the fact is that now we can actually look at the data and let it speak itself in multi-dimensions rather than these kind of more traditional decision support tools that have kind of restricted us. So yeah, it's a very exciting time, but it's been through my journey both with renewable energy siting, for instance, where there's a lot of multitude of factors, but also 8 years in transport planning, where again you're working with the environment, the built environment and infrastructure, and trying to balance all of that as you help policymakers decide on where and what to do with investment or where needs fixing. So it's actually built up through that 10 years of experience of realizing we have these questions. And before that, I had another course which was on sustainability and corporate social responsibility. With sustainability, you always have a triple bottom line. Your social, technology and environmental factors all have to come together. So then you automatically get these multi-objective problems, and that's what I'm hoping I've found a framework to provide as a robust way to handle these.
Yeah, that makes sense, and I love that example of a very tangible sort of multi-objective problem and where, as you say, it's easy to do things that aren't so sophisticated because of that complexity, and actually there are ways of attacking it using a bit more sophistication, using a framework that really lets you get something out of it. Brilliant, thank you, Pippa. I think that you've answered really nicely. I really enjoyed that, and I think we've thoroughly set the scene, laid out the red carpet for spatial data science to step into the spotlight and shine. So I will now hand over to you for the presentation. Thank you.
Okay, great. So as we touched, there's a little bit of a highlight of my career, but yes, I've been in GIS and spatial data science for 10 years now. But before that, I did have some background in the sustainability sector, as well as international relations. So a bit of a mixed bag, but my LinkedIn's there if you want to find out more. So today, going to set the scene a bit about geospatial, and then tell you a bit more about the solution creation of Cilla, and then this case study to really put spatial data science in action and see how these models can be constructed. So first of all, for those who don't know much about geospatial and location data, geospatial is anything to do where you've got coordinates or a location on the globe. If it is that kind of data, then it's geospatial. GIS is typically referred to information systems such as websites, apps, databases, and core platforms that look at different types of spatial data but can also interact with different relationships. However, GIS is really starting to happen outside of traditional GIS tools, and this is what I was mentioning about this change in the industry. Now that we've got more advanced spatial analysis at the same time as we've got access to data science and big data solutions, we're now seeing this shift and actually a new discipline of spatial data science emerging because of this link with open source and cloud technologies. There's a whole myriad of key benefits that at PA we're able to unlock for benefit client delivery and also internal business development. In particular, we've got quite a new group of GeoPA group, which looks at, which is a group of GIS and location intelligence specialists at PA, and we can help build such geospatial solutions and develop data-driven strategies to really help our clients and unlock that location potential. So just a little bit more about GIS and spatial data science. For those of you who are data scientists, you'll be probably quite used to this model of a three-dome model of computer science is a mix, data science is a mixture of computer science, statistics, and some kind of purpose or business domain. However, with spatial data science, what we're doing is making sure we've got this geometry part fully integrated, where we really understand the laws and pitfalls of geospatial whilst we're doing these techniques. But for the GIS people, professionals, they'll much have their own set of tools and a business case, but they'll not always use much computer science. They may start to automate a bit with Python, but not to that level of the data science approaches. And so with real automation, you can start to reproduce exactly in a consistent way your workflows, update them, and have really overcome interoperability challenges as well. And also this can allow you digital app development and API development because you've got that core programming background. Without that, you can't really shift from the old type of GIS into this data science world. And then on top of that, there's a different level of statistics. We do have some geostatistics specialist concepts that you have to understand within GIS. However, with but with a much higher level of statistics, you obviously can integrate that with computer science, which is all about your machine learning principles and your algorithm development. So that's really, really important that you have that depth of knowledge of computer science and stats with the spatial. And that is the difference between typical GIS professionals and this spatial data science that you're hearing more and more about. So what tools and techniques, if you want to get involved in this game, what do you need to be able to use? So Python is a huge dominator of the tool set in ways that you can script outside of typical GIS platforms. The GIS platforms are still very important. There are certain relationships and understanding processing tools that are very, very important in still doing certain manipulations. But things are developing with Carto and within Esri to integrate those more and more with cloud platforms and with Google as well. Another area is R. That's very good for geostatistical purposes. A lot of academics use it, and there's some great apps that can be developed all in one place. I'd say Shiny's great if that's the environment you work in, but you tend to have delays compared to being able to actually use Python and straight into JavaScript technology. And then finally, databases. Databases are very important, core of data science, but there are specialist ways to integrate that as well for spatial, especially post-GIS and post-GIS is part of that. And finally, it's not all just about the analysis, also about the visualization. What's the point of having really amazing analysis if you can't show it off? So this is where web mapping becomes part of its own, either integrated into other apps or dashboards or in its own light as a way of demonstrating analysis results. So there's increasingly more web mapping options out there, but you can also just customize from JavaScript, have full customized options by being able to code at that level, but by bringing it in with platforms such as Mapbox that give you the viewing windows. But what's really quite interesting is there's actually still only a limited number of me's out there. There aren't many spatial data scientists who've got that very intense background in GIS mixed with the data science. There are lots of data science though trying to do location. So there's actually only about 1 to 5% of data scientists that have got this kind of specific background. And we're just hoping there's enough of us to spread the word and train and educate others.
That's what today's all about.
Like today, yeah, exactly, getting you on board of doing things right. So yeah, obviously at PA we do a lot of offering, but today I'm focusing on spatial data science, but we do obviously work in lots of other technologies and offerings, remote sensing to network analysis. Some examples of cutting edge technologies that are out there, just to kind of put all this into context, is you're starting to see a lot more in city science and active travel with AI sensors, and more that we have sensor data and Internet of Things, we can get real-time updates and analytics. This is actually quite exciting, and we've done things in this field as well at PA. And secondly, LiDAR data that gives you very, very detailed object identification and information is really helping with things like autonomous vehicle integration, to know exactly where those barriers are that need to be dealt with the autonomous, make sure the vehicles don't bump into anything. So, and then finally, a good example is agent-based modelling, and this is where you measure emergent behaviours from a model, and this can really help you in real life know where those tolerance levels are within complex systems. Even evacuations, knowing at what capacity does a station have to reach to when you've got an actual problem with an evacuation versus when it's just very, very simple to get everyone out. So this can be really, really important, especially in kind of complex situations in cities and traffic management, which I think is what was part of this case study mentioned here on New Zealand, the kind of work they're doing. So it's quite a bottom-up approach, but it gives you this like, high-level emergence that can really be insightful, especially with rebound effects. So yeah, just wanted to check in if there are any questions on the background before I move on to solutions.
We've got nothing on the chat at the moment. Are there any particular questions in the room? I can relay them over to Pippa. Looks like we're all good for now. And so we will be able to continue in a second.
Okay, great. So yeah, I'm just going to tell you more about this Cilla idea and the strategic investment location analysis. So first of all, that kind of governing thought is really that client challenges and customer challenges involve these complex systems and multi-objective questions. As I mentioned before, we're working in the real world with complex systems with operational investment network performance. And it's just important to have the tools to answer these problems. So really understanding today about when you need a specialist set of tools to integrate with what you're already doing, but know that they are there to help you. So really what we're asking is how can spatial data science provide these solutions and harness that transparency and also deliver insight into into the findings. So the answer really is innovation, and that's something at PA we really embrace. So geospatial analysis is inherently designed for transforming and consolidating vast amount of data. That's what GIS has always been good for. So why on earth are we not bringing that more into our data science world? So these kind of workflows I'm going to show you today integrate that analytics so that we thrive on the data science approaches we love and know with this deep data investigations that can then inform that locational based decision support. So we're going to split this the rest of the presentation into 4 sections. So what is Cilla? There's going to be a video in a minute. Why is it needed? What have been the limitations of everyone else's previous approaches or the core approaches, the research gap? And then how is Cilla actually applied? So I'm going to take you through the case study. And finally, how can we actually present our findings? And there will be a demo at the end to really understand how these web mapping tools can bring your data to life. So here is the, going to be a little video they made to try and bring a framework to life.
can get the bar up at the bottom. Uh-huh.
How do I get? So I hope you enjoyed that little video, but the real headlines from it is this is an opportunity to really have an end-to-end spatial data science framework that solves multi-objective problems with actual boundless choice in the number of parameters. It's all about letting the data speak for itself. We want to group together the data points according to the intrinsic similarities between them, based on the idea of using clustering, and finds those similarities in the complexity. Then the locational part is that all the spatial units are then unified in the geometry, so all the parameters become comparable within that aerial unit with no aerial distortion that you get from using mixed geometries. The spatial distributions then can reveal those location insights, and also within the classified groups we can then start to identify locations for mitigation and investment. And finally, the spatial interaction of the reporting using the Kepler that was shown here, as well as there was a Power BI example as well, starts to really help you drill down into your results. So I'm going to quickly pause in case there's any questions there. If not, I will talk you through the example and also move on to why this solution is needed.
Great.
Okay.
We're all good in the chat for the moment. I'll just check the room if anyone has one. Looks like you're good for the moment.
Cool.
Good to continue.
So why was this solution needed? What was that research gap? Well, really, it was about multi-criteria analysis. That's a decision-making framework usually used to solve these problems traditionally, and it provides a systematic approach, but it uses rankings to make those adaptation options, and it also weights them, so it reflects, so that someone decides how important something is relative to something else. And usually when you do that, you have a stakeholder engagement meeting, or key stakeholders get to choose those help towards making those decisions. So in fact, they are already making those decisions without really looking at the evidence, within the evidence, the deep insights that could have actually informed those decisions. So it's all a bit biased. So the limitations are that you get the good, and also when those are combined with red, amber, green RAG ratings, you get a very simplified result. So on the left, is an example where kind of MCA approach has been used and the RAG rating has been used to present those findings. And what that gives you is the good bits of a network and the bad bits of the network, and it can look a little ugly. So that can be very, firstly, oversimplified of those kind of 3 colours isn't enough to make any meaningful decision. But most importantly with MCA, a single score is used on an index. And as I mentioned before with spatial, you may do that using map algebra. But the issues are those areas actually like for like? So if you've got an area that is 5, 5, 5, 5, that's a score of 20. But in one area, you've got that score. In another area, you've used the same 4 parameters and you got a 0, 10, 10, 0. So in 2 places, those parameters are non-existent, but you've ended up with the same score. So how is that actually fair with the model? And then on top of that, you're making some decisions on those scores. So clearly, you're going to have issues. And who decides on those thresholds and those weightings of what has already been a simplified scoring system? So and the final point on RAG ratings, and where you've got or an indicator that's good to bad or poor to favourable, you start to maybe detract investment. So in this situation where you want people to invest in improving the city, you're actually saying, we want you to invest in a place that's got a bad indicator. Instead, they want to really understand the inherent characteristics so that they can improve that area, not just be told, and so it will detract from that. And then if you haven't got people investing in your area and neighbourhood, then that may negatively impact your house prices, all because of a RAG rating that started the process. So, so that's really important when you start to make decisions. So the other side so that's the main kind of research gap. Cilla's also been used not just in the project that I'm going to showcase, the original research, One Healthy Streets. This was done for the whole of London and benefited UCL and TfL and WSP. But as part of that, the Cross River Partnership project was happening at Momentum Transport Consultancy, and they wanted to use the actual model the finalised model to look at specific places and specific sites to see what the model was saying and whether that should be an area of improvement. And they wanted some empirical evidence basically to support the decisions they were already making. I will show you briefly those results at the end. And then finally, it has actually been used. So we're going to be looking at a hex level full surface model of the whole of GLA, so the Greater London Authority. But it has been used on the whole national strategic road network for national highways. I cannot go into the details of that work, but the fact is that it can be used on links and with line connections and network analysis equally as when you have a full plane of hexagons. Finally, in PA, we have in the past done something similar with clustering algorithms and location data. I think it follows slightly different methodology, but these kind of ideas have already been emerging from the company. And in this particular instance, was to do with more incident clearance times that got reduced by 17%. So clearly, putting location and data science together can make some real changes for our key clients. So I'm going to tell you how Cilla's applied by using this case study. So first of all, some intro to the actual case study. So the situation is that the Mayor's transport strategy for London is that 80% of all trips need to be made by foot, cycle or public transport by 2041. Obviously that in turn is kind of linked to net zero targets. And the way they want to analyse the streets and where there needs to be investment or to make the streets more attractive for people to use for cycling and for walking, they came up with this composite model. So it has 10 strategic objectives that you're trying to amalgamate all these ideas into one metric. They have, obviously this is a great example of sustainability and sustainable regeneration, where you clearly need to get all these factors together into one method, and they designed a toolkit. And you think, oh great, that's really helpful. But it was designed for street by street surveys. So you get a list of questions and you have to literally answer all of that in relation to all these indicators street by street. However, so obviously you need a strategic approach, but there's also there's even more relevance on this healthy streets approach, because not only has it been adopted, it's actually been stipulated in the London plan that it must be used, not the actual toolkit, but this approach of these 10 factors must be used to deliver anything that's public realm and new developments in London. So likely this is going to probably expand nationally and maybe something to be used by all planners and planning development. But planners will want to know about a borough, not every single street in that borough. So it made a need to actually find a strategic solution that was a data-driven decision-making approach that could actually look at neighbourhoods, intra-city level, and as you'll see, it can scale all the way up to insights for the whole city. I should just note here that 4 areas couldn't be fully considered. This research was all done during the lockdown of the pandemic. So in certain areas, there may not be very clear data available and where surveys would help. But those restrictions, haven't impacted much, but it's worth mentioning. So the complication, as I mentioned, was this toolkit that allowed you to do street by street. But made worse, it was the score manipulation. People said they could just change all the outcomes in the Excel macro to basically get the favoured outcome to help the developer say, oh yeah, this is going to be great. And you can start to see why. Well, actually the funniest thing is, number one, as you would have seen back here, is the purple pedestrians for all walks of life. They have got no limit, so all these 30 questions, they all link to specific description of data that you need to use to answer that question. And there was not one link to socio-demographic data and socio-economic data, but they want to have assessed the whole of all people from all walks of life, and not even know what the population is in the area, because they're looking at the single link on that street, but doesn't help you understand the neighbourhood. So the other main thing you'll see is, oh my gosh, what are all these ticks? So you have got, for every single question, they want you to consider all people's walks for life. Why don't you just say, okay, they may have put some different weightings, because it's MCA, in the back of that, but they're basically saying, yeah, that's a really important factor to the mix. Similarly, you've got the same happening on 6, 7, and 9 is just as horrific. So basically, you've got this multicollinearity going on in those weightings, as well as horizontally, where you've got multiple indicators for one question. Yep. Surely that question should just be linked mostly to transport safety or the people who live there. So I reworked this with each question was paired to a national or GLA data set, so we could look at the whole of London and potentially upscale. Where possible, open data's been used. I think open data fully resulted from the 28 parameter model. And then we've broadened out the parameters by using socio-demographic data. And in the end, if you mark these up, you get a 50% split now between looking at transport and environment factors and socio-demographic inputs, which ultimately, when you're looking at active travel, and you want to be thinking about transport and you want to be thinking about people. So that was the main change, and to address that complication. So how did I move from that into the actual product development? So the most important thing with data science generally is to follow a really good end-to-end workflow, and that it instills best practice, and you can't get lost because you know where you are in the life cycle. And it helps the analyst on that systemic journey from data gathering all the way through to delivering that business insight and digital solution. And it's quality assured because your client can see exactly the journey you've been on, and you haven't just been manipulating the back of Excel spreadsheets. So the data choices I've already talked through, but you're basically consolidating those indicators, removing collinearity, identifying missing metrics, like we found there was no socio-demographic data. Look at the provenance, make sure the years, and because it's not just spatial, it's also temporal, make sure the data you're working with is all going to kind of year match and be roughly comparable. Look at that metadata and data sources, think about the year, also the license. With there's a lot of open data out there, but for spatial there's some very, very good open data that comes specifically from our mapping agencies, and it's really useful to use that in the UK where you can, and that will indicate your client use. So you might be able to use it for private and public work. Public sector tend to have their own access to further data, and make sure you know about that to really embed that into your models. So on the data science side, there's firstly your typical data science, what we love, bit of Pythonic munging and testing. And those kind of tests that I'm sure you'll all be familiar with are making sure you check your distributions, you check that missing data, you look at outliers, you scale the data if you need to. And what I love is these kind of correlation matrix, brilliance, Seaborn type visualizations that can really show and test that multicollinearity, and where you can start to see that this is before any changes, that yellow brick is like 3 different parameters on demographics that are all quite similar. I think they were to do with age ranging, of using aging population or young population, and realizing actually you only probably need one factor there. But if you don't do the data science, how do you know to make these changes? So then you get your robustness, you get your better insights, and then things at the end are all going to start to look great. And most importantly though, by doing this you'll get that comparability between the data science and when you've worked on the spatial unit. You'll see in these results actually there's quite a lot of skewed data. So taking logs to prepare the machine learning model that comes later was absolutely very important, and really affects the algorithm choices and whether you're using those algorithms on your standard scaler or need a different scaler as well. So unless you look at these checks and you visualize, you're not going to get the results you wanted. So the next bit is the spatial data science. This is a tiny bit more complicated for those not familiar with spatial, but hopefully this will be clear. So if you're working with a lot of data and you've got lots of different geometries, you really need to have something that's united and one unit that will take you, so that all those different parameters are the same within those units. Obviously it's a form of normalization, but it's absolutely critical. And this is where the good old hexagon comes along. So I don't know if any of you know about hexagons are the bestigons. Please go into YouTube now. It is the best video ever. We didn't really have time to show it to you today, but if you want to know about honeycomb and the hexagon on the top of, I think it's Saturn, yeah, absolutely best video ever. But in summary, what it's telling you about is why you want to bin and work in grids, and then some of the hexagon rules. So a grid is brilliant because it provides this equal density of your data spatially. You'll be familiar probably with lots of projects that use those ONS census units, LSOAs, MSOAs, that especially when you've aggregated maybe health data recently, they work in all these areas, but they can cause real problem. Firstly, they are not uniform, they need normalization in different ways. You have the good old mapping aerial unit problem. This is where things can stand out and look biased because they're a bigger area. So for instance, if you color up a larger county like Somerset, that kind of stands out when it shouldn't. And this is how there's some really good examples by Monnier of kind of the election and political maps. And it may look like a victory on one side by looking at the map, but it isn't really, just because of the size of the units the data's been put into. So it's really important to get this right. and then you want statistical robustness from that into any data science models. So the other thing is obviously get computational efficiency because you've got those simplified edges. So what's so important about the hexagon rather than a normal square grid? So it reduces the sampling bias from edge effects because you can actually, you can only tessellate three things, a hexagon, a square and a triangle. But this has the least, as the most representative circularity and the curves, so you get the closest fitting grid. The most important thing from a spatial angle is about the centroid. There is no distortion within a hexagon. You have always got the same distance going out from the centre than you do with a grid. And this is actually all about, and also your number of neighbours. You've just got 4, now you've got 6 to optimise on this. And when you're looking at spatial distances and looking at things, this really makes a difference. And if you think about chess, you've got the rook's case, you can go up and down, side to side. That distance is just n unit to go in that direction. When you go on the diagonal for the queen's case, which is the other way, you can also look at distances potentially. That is already the square root of 2 n for the, and as a result, those distances are longer and they're distorted. So this really does start to impact because you're already looking at the problem potentially with machine learning in your like 28 dimensions, and you're adding that inconsistency with your the grid that you've used with that for all those instances. So hexagons really are the bestigons. And when you're working with much larger areas of the whole globe, which obviously we know is a spheroid, you get that distortion effect, and you get that less when you use hexagons rather than a normal grid. So a tiny little lesson in geometry types. There's only 3 types of geometry of which you do all your relationships and all your analysis with. You get points, you get lines and polygons. And your points, well, they're easy. You just sum them up, chuck them in the hexagon. Lines, really easy too. You just break them at the edges, sum them up. Obviously, you can do slightly more complex things if you need to, but that is the basics. But with polygons, you've got alternatives. So, because we're trying to put everything into hexes here, you can use percentage overlap or asymmetric mapping. Well, what are these? So, percentage overlap, you'll probably be most familiar with. It is the area that overlaps into the area that you are measuring. So here, we've probably got 33%, like a third in one and 2/3 outside. And this is all good if you've got a homogeneous variable that you're working with. But what about population? In population, you're likely to need something that's weighted because people don't live evenly spread. They're very much unevenly distributed, and there's a lot of things where you may want to know where things aren't rather than where they are as well. So you need a grid that facilitates this data conversion. So here are all your houses, and you've got nothing in the polygon. So a asymmetric mapping technique will give you 100% outside, but basically 0 to your polygon. Whereas if you're using that normal percentage overlap that you think is, oh, that's great, just chuck it over the top, you've already given 33% of that unit's data into that polygon. That can cause issues. So during this research, I actually developed this new open data method because I wanted to respect those areas of no population, especially in London, where lots of other techniques tend to put data where you don't want it. So basically, you've got here Green Park. You really don't want to be putting people in the park. You also don't want to be putting them in Heathrow Airport, and even in main stations, you really don't want that allocated. So the great thing is, to do this weighting, you really need the property granularity. And because of the great efforts ordnance surveys done with the new Geospatial Commission a few years back, they are trying to get more open detailed mapping products out there for free. So with the OSUPN, you get every single spot for every single property. it doesn't give you any of the attributes that you usually pay for, but you know where those properties are. And in a block of flats, it doesn't just give you that block dot, it gives you, say you've got 8 flats in your block, it gives you 8 dots. So that means when you add everything up, it is actually proportional to property. So although we couldn't, with the open data you can't choose between residential and commercial, the results were still fantastic, because this is more granular than you're used to. So what I did was TfL had already populated these hexagons with datametric mapping, but with the paid address space. And because I had a research license, I was able to do a comparison. So first I took percent, this is just Wandsworth. First of all, I just took the overlap of the census output area, the most granular level, that's what these green lines are, and I just did the percentage area overlap. You got some huge gains and huge losses from their results. I then did it with the OS Open UPRN method, and you very much have got the same as that address base. Difference is I haven't paid thousands of pounds for the whole of my London data. What this means is regional analysis, and where we need to do this strategically and possibly nationally, becomes viable, and you're going to get better results for those demographics. And demographics here is really important because, as we said, we've now weighted, well, not kind of weighting, but we've proportioned the factors to be half transport, half socio-demographics. You got that socio-demographics wrong because you've gone and put people in Heathrow Airport that are, well, I mean, actually living there. Obviously, there are people in Heathrow Airport. But yeah, then you've got an issue. So this really mattered, and these are the results. So we have got 15,000 hexagons. There's a 2.5 minute walking catchment. This was chosen because this is the granularity that TfL have also been working on, and they've got an open grid that you can use. So what these are the results as a detailed mosaic that you could go down to that granularity, but by using strong contrasting methods, and this is where visualization can start to really sell your results, you can start to pull out some of those patterns and also notice that in all of them, we've not got data in Heathrow, we've not got data in the river estuary, we've actually starting to look at all these barriers, physical barriers in London, and also infrastructure barriers, and respecting them in the model. So when this starts to layer all these layers together in your machine learning, you're going to get a really powerful analysis. So this was, the results for the socio-demographics. There were, as I said, there's 28 factors. This is just obviously 6 coloured in, and you can also start to see the intensification of densification of population and different factors in the inner part of London. It's already telling you that when you see your model results, you should start to see differences between inner London and outer London. And if you don't see those, you need to ask yourself why. So again, if you're not looking at the spatial of your data, you'll miss some of these subtleties. So the other set of parameters were to do with traffic and environment. Again, the little hexagons all join up and look very nice to reflect the impacts of pollution, or also the amount of road flow. The flows have all been aggregated, and they're starting to make sense because when they're put together, they still look like a road network. In order to do that, there was quite a complex real geography transformation that has to happen to put all your DFT counts onto your major roads. That's a process I've developed previously, and I'm not going into today, but there are ways that if you've got point data to get that to connect into roads. So now we've got everything ready. We have got all our data science checks done. We're happy with our parameters. We've got all our data into hexagons, but next we want the fun. Where's the real data-driven insight? And this is where machine learning can just transform that offering. So in this process, where it's slightly different to others, is it's a 2-tier algorithm approach, does HDB scan and then k-means. So rather than just relying on one algorithm to do all the hard work. So first of all, the HDB scan works really well as it's hierarchical, and DB scan's always been known for being very good with distance. And so this helps find all the outliers. Outliers can be the most important part of your data set. It can actually be the thing with the most valid groups. So you want to work with those and see if they mean something on their own accord. But the quality checks are really important with doing and quality assurance, because the more black box work we do as data scientists, the more lost our audience can become, our clients, our supervisors, of actually how was it done and is it any good. So it's important to keep silhouette scores and dendrograms going with HDB scan, and with k-means you very much want your elbow plot as well. So first on the HDB scan, it's really simple code. You've literally just you've only got 3 parameters on this one, and you can only really change the epsilon. And you just play with that until you everything kind of makes sense, but you can measure that against your silhouette score. So I think my bar at the bottom just knocked that off. But you have very similar set of results with the k-means. But first of all, you usually always do an elbow plot. And this tells you at which juncture you should, number of clusters you should try out. In the end, because we've got that spatial angle, when you map those results, it started to make sense to have a slightly overfitted model, because you've got quite a few of those groups that are going to be where there's no people. So where you want real meaning, it's made sense to slightly overfit the final model to 6 from this area, but for this particular algorithm. So yeah, and so therefore you run one, and then after you've got that group out, you can run the next on the whole mass. And that's really important to do the k-means second, because then you've got your most spherical mass and your point cloud division, because k-means doesn't like extreme values. So now you know that not only is your spatial data science, your spatial, really, really well thought through and been unified in the geometry, you've now got a really robust situation going on under the hood. So but how can you present that back to someone who's not data sciencey? So remember, visualization is everything. So this is actually the point clouds, and you first have those outliers, so you can start to check that they really are outliers. To do these visualizations, for those in data science, you'll know that you cannot look at a map in 28 dimensions, so you use dimension reduction, and that's how these 2D plots are made, but you can make 3D plots if that suits your data, and they're quite cool to work on in Plotly and get people again interactive in your notebook, understanding your data. So yeah, then the k-means comes out as that white section that gets run through, then you've got your 6 clusters. But then what does it really mean? Because we want to understand, so every point on here represents one of your hexagons, each hexagon. That's why we've got 15,000 for the whole of London that we can test. This is a really, hopefully good, robust granularity model. So for every single parameter, you're now taking that in, by looking at heat maps, you're now creating this perfect like DNA profiling. And this is the difference where MCA gave you a score. You now have this similarity areas that have high population but high issues with safety, road safety, noise, maybe poorer, lower index multiple deprivation. It's all then there, and then you can work out what these all represent. And yeah, some will have low properties going on, and you can start to make descriptions for each of these. So then, of course, you want to map it. So later I'm going to show you about putting the results in Kepler. But just for now, I'm going to just talk through the real high-level findings. So this is what happens when you map it. This is how you start to bring that data science alive, because every single instance in your data frame wasn't some weird census unit. It was a hexagon, a nice clear hexagon, so you can easily see equal density and the real patterns start to jump out. You can immediately see that you've got some inner London behaviours going on with outer London. Therefore, we can start to, I've made full descriptions of each one, but you can start to think of some punchy names for your clusters that also link spatially as well as those characteristics. So we've got our suburban areas, and as well as your kind of inner city. The green is actually picks up high streets, so that's quite good because you should expect your green to run into the suburban as much as it is an inner. And no man's land is being respected. It is your grey, the greyish areas here are clearly your Heathrow airports, and your the River Thames is also respected, and your parks. And so this is really good. I'm going to go into a bit more detail about arterial connections and mobility mayhem. Those were our two outlier groups. Those were where things were really, really high and probably really, really bad and need addressing. So in Kepler, I'll show you in the demo, you'll be able to filter your data table. So if we filter out mobility mayhem, this is basically that spatial decision support that you want to take those areas, and this is where the investment location analysis comes into it, because now you can say these are the worst areas, these are where you need to invest, these are where you need to prioritize, or at least ring fence to now look at, are there other factors to explain those that have not been considered, but we think these are areas of concern. And then with arterial connections, really interesting one, because you'll think that, oh, these are all the main radial roads going out of London, and you've got the inner and outer main ring roads. And so, sorry, the north circular and south circular were the words I was looking for. But you've got these other specs, and it's like, well, what are they? Well, they are actually, because the way a machine learning model works, you've learnt what roads are, but you've also learnt areas that you think are main roads, and that becomes really, really interesting. So if we take Wandsworth again, which was actually my original case study because someone said, what can we do in Wandsworth? Here we go, we get multi-scalar insights. So all those hexagons come down into this. And this is just brilliant because you've gone from that strategic view into this area. And we know in Wandsworth, if you're local, that there's some key arterial roads going out, the A3 and other roads out to Wimbledon and the such. But you've also got this area of main high street area down to Tooting. And it flags that you've actually got a real issue just south of Wandsworth Gyratory, and you've also got some real issues down in Tooting. So this corridor was actually the area of interest that sparked this whole project. But what is this brown dot here? This is between a residential area and a high street, and you've actually got schools there. It's actually a rat run, so it's got too many cars on it, too much pollution, too much noise. All that data's come together and learnt that that is a problem area within your data. So you'll see that there's a really nice heterogeneity here. You haven't just got huge areas of one similar area. You start to get these little gems, and that's why the red mobility mayhem starts to give you those insights, as well as these bits of main road that aren't main roads, and other intricacies. So yeah, it all starts to come together, and you can work, and you start to answer that question: can I apply the healthy streets approach with different set of data, actually get insights that's going to help someone go into your borough and make differences? Yes, it's going to make the engineer consultancies and other people that get commissioned to go and do surveys to be like, well, how about we start here, we go to this one, and we go to this area, and go and do the full Healthy Streets toolkit. This isn't saying you don't need that toolkit. You will need it for your master plan. But the question is, where do you start?
Yeah.
So now you've answered that. So I hope that's real interest. So the last thing I mentioned, I mentioned from the model, was this piece of work for Momentum. And it was basically taking those model results, zooming into very specific sites. And because we had that granularity from the beginning, even the smallest site of just a few roads we get some interesting answers. So we put in as a 2.5D footprint over the top all these different sites. And as you'll see on each one, this red mobility mayhem area appears next to the high street type behaviour on every single site. So they were absolutely so pleased that they had now some empirical evidence that they needed to improve that part of the public realm in order to get their planning permission with TfL or with GLA, because they need to, because developers need to help create sustainable regeneration rather than just make the nice places nicer and let the poor places get worse. And then they wanted to pull out these specific factors as well. So you can look that the population density is very high, so it is affecting areas that's going to have the most gain for those neighbourhoods, as well as the deprivation layer that shows you if that's a little bit higher in deprivation to the north of some of these sites, really deprived up near Atlantic Road. So that shows, right, this place needs investment as well. So you can start to drill in to make sure that your classification starts to make sense. And especially the ped and cycle casualties has been a really, really important one, that with active travel, you want to gain that trust and get people to shift in modal shift in transport. And now you've got something that also fully reflects that. So just to round up on all of that, I hope you'll see that I've addressed some flaws in the original Healthy Streets toolkit. I've looked at that non-populated weighted analysis issue and why it's important to fix that, and the issue of not having unified spatial units. Also those weaknesses in the multi-criteria decision and those subjective indices. So my solution was a 28 metric data catalogue, fully hexed and fully homogenized and population weighted approach. Then you take the spatial intelligence on top of that with your machine learning, clustering and profiling. And on top of that, you can interactively visualize and report that. And as such, you can then look at things at multi-scale. So yes, that is it on this, on the whole Cilla. So yeah, any questions? And I hope you've enjoyed that run through of this spatial data framework.
Brilliant. Well, we wait to see if any questions come from the chat. If anyone in the room has any, I'll relay them over to Pippa.
Yeah, awesome to hear all of that, Pippa. Just one question around, I can get how you can use hexes to understand all of the areas around London. How does that change when it's like a, I don't know, road network where it's all long lines rather than areas next to each other?
So just to relay the question for the stream, sort of the audience member asked, how does using hexagons to map out areas such as you've presented in London change when you're dealing with things like road networks that are not these big planes but are smaller, thinner, sort of less connected elements of space?
Yeah, absolutely. So this is kind of what linked to the pre-processing stages was slightly different with the National Highways example, because so basically when you deal with networks, you want to really work in links, because a lot of the data needs to be linked to that. If and that's the most important thing. If you were to use hexes, you'd have a lot of empty space that wasn't relevant to your highways agency. So you'd remove that. If you keep the hexes along just your network, that can become potentially problematic with highways because it picks up land that's not theirs, and so there's that. And also, but with energy networks, for instance, if population areas interest, but energy is another big area where you'd want to work with links. So really the pre-processing becomes more of your typical normalization processes. and you'll probably be normalizing mainly on kilometrage. With transport and traffic, it's slightly more complicated, but the good thing is RTM, road traffic models, they're all calibrated so that each link is comparable, because they know that on the strategic road network all these links are different, and it actually takes it into account. And it's very good if you can work with people who have those detailed niche skills in the data already that you're working with, so that you can carry on their practices at the same time, and make everything comparable. But a lot of units may need to just be limited to like per kilometrage, but sometimes you want to weight that on some other factor. But yeah, you'd normalize the links, I think is the short answer. Sorry.
Yeah, fantastic. The detail is really appreciated.
Yeah.
Any other questions from around the room? Great. So it looks like that might be it for now. I guess from my part, I want to say I'm a bit of a mark for this stuff because my background's in geometry. So as soon as you started talking about points and lines and distances, I was like under the table. But what I will say is I sort of love the Cilla framework. I love this idea of knowing exactly where you are within the scope of doing something. You're not just throwing stuff at a wall, but there is a process and it's important, and it factors in the things we know and love and we talk about a lot when you're working in data science, but also this inherent otherness of there's this spatial and it should be considered. And I really enjoyed it and felt the Healthy Streets example was a great way of actually showing how it has the power as a visualization tool to really take the end user along with it. So yeah, big thank you to Pippa. We're going to take a break now in person so we can go have some pizza. And then afterwards Pippa's going to deliver a live demo of how we can actually put some of this thinking into practice. For those of you at home, you won't get to enjoy the full sensory experience, but we have prepared a pre-recorded demo so that you can follow along and actually see it in action. So all that it stands for me to do is say that we will be back again on the 21st of December for our next pizza session. The topic is yet to be announced, but look out on the Meetup network or YouTube to see it first. And otherwise, big thank you to Pippa for the presentation today.
Thank you.
And with that, we'll pass over to the
Hi, I'd
demo.
now like to demo Kepler to you. This is the web mapping application that was used to present the results that we've just shown you in the Healthy Streets images. This is a really, really great web mapping application. It is very quick to set up. It's open source and you get your visualization just in minutes. It's got some great features that we're going to go through, especially comparison view, which a lot of web mappers don't easily let you look at two views at the same time. So I'm going to show you some of these results of my model, and then try and give you a chance to learn how to do your own. But it's really great at really selling all that spatial intelligence that you have built within your machine learning and data science models, and actually bring this data science to life. No one just wants a flat map or a flat plot. They want to be able to really embrace with your data. So I'm just going to start up that model, and the output of Kepler is just an HTML file. So you then have that for your own devices and can run locally. So here we have the main outline. So we're looking at the whole of the London results strategically. And what's really great is we've been able to set up some different layers. So as you know, there were 28 parameters in the model, but now we've got just 4 set up for you already to have a look at the results. And then, so for instance, there's no car households, cycle kilometers per hexagon in London. So we can just see that to one side. You can also overlay very easily both the schemes that are in progress with TFL, and this has been really good as validation layer both to the results but also how the individual parameters are working. It's very easy to set up a tooltip, so for every single hexagon we're reading the data, and we've got this limited to the corresponding cluster name and some of the data values. To set all that up, it is really quite simple. One thing I will just show you is when you zoom in with height extrusion, you may want to be able to turn that off to look at individual factors. So this is all very easy to edit. You've got your layers for the no-car households, for instance. Just at the bottom you have a height level that you can change and set as required. The other important thing is the tooltip options. So this allows, this is where you can then choose which columns of your data frame you want showing for all your different layer options. There's also some other options in here for geocoder if you want to be able to search places. That's where that's set up, and filters can also be added. So this is really useful. I think in the my results I showed you where we had just the certain layers. So if I put the legend over here, if you remember, I talked to you about the mobility mayhem layer. I also talked to you about the arterial connections layer. And this is how you can just very quickly filter the columns that you want from here. Just add that filter and select that field. And then you'll be able to look at the individual layers on their own. So it's all well and good looking around someone else's model, but what if you want to actually create your own? So what we're going to do is I'll take you to the Kepler website. This is actually a really useful tool, and it's not just for showing results but for different purposes. So you might already be really interested as a data analyst, or even at a strategic level where you're trying to show off your results to that client who only has an attention span of a few seconds, and you just want them to think, wow, that's what my data looks like. So it can be used for so many reasons. But if you are that data scientist, not just a map enthusiast, there's a lot of examples on the Kepler website, but the data scientist side, you can now integrate this into Tableau and Jupyter notebooks. And then you can also embed it, and also because you've got the HTML code when you've completed your kind of quick prototype, you can add in your own functions. For instance, although there's a spatial temporal option built into Kepler, you can actually add those time frames, I think more simply with a bit of JavaScript. But it means you can make customizable websites, or you can start bringing this in as part of a solution and not just have to work from the web map interface. But yeah, we're going to create our own. So we're going to get started. The only thing you also will find you'll need is a Mapbox token, which if you just sign up for Mapbox, you can easily get so that you can save your HTML files. But that doesn't stop you from getting started. So we're going to, got a good example here about closed schools in the UK. So what this actually does is drag and drop CSV or JSON or GeoJSON files. But with CSV, we've just got the points, latitude and longitude. Really important thing with the web mapping is you need your local coordinates to be in lat and long, not in X, Y in the local system, so it can work on the global projection that we use for web mapping. So if you've got all your lat long points, you can start to look at the data. Oh, this is very interesting. This is all starting to look like some points, and you can understand their distribution. But what if we just want to understand a little bit more? So it's very easy to duplicate layers. So we want to keep the same data, but we want to do something a little bit different with it. So we'll hide the point data. I'll put on the copied layer, and the first thing we're going to do is it'd be useful to have more of a heat map. So you just select the heat map, and then you can start to see those areas. But heat maps are great until you need to, you can't really do much interactivity. We may also change the color over here because it's more intuitive that where you've got a less count, it's cooler, and a cool color like blue to red of the heat. So we'll change this over, and it becomes a bit more vivid as a visualization technique. But yes, it's very easy here, as you can see, to change your colors. So, and also it gives you some added insight to visualization types. So you can see all of them, but if you want to understand about visualization, you may have something that's diverging, sequential, or where you want a single color ramp. You can also limit these to those options to help you with those decisions. So the heat map here, we've got sent, but the thing is, it's not really that interactive with the count points or anything. It just gives us an idea of the distribution. So wouldn't it be better to have a bit more local interaction and actually see what those counts are? So we very quickly can just duplicate the layer again. I'll just make a note that this is the heat map. And this one, we're going to try out hex binning. And this can be done on the fly. So you just choose, because you've got your points, you can choose the hexagon. There's also grid options, but as you learnt before, hexagons are the bestigons. So we're going to do a hex bin. And I'm just going to turn that off. So if for any reason it's not automatically reading your Latin long, you just need to find it. Yeah, now you've got hexagons, but you can't really see them, so you can custom size to what you think is correct for the grid. So this looks like a good size grid to see things strategically, and you can start to see the clusters around London and also Manchester and the Midlands. So this really helps, because now you can zoom into an area and you can actually start to get the hex bin totals, which you couldn't do on the heat map. And you get that specific location in sight. So this is really great. The next best thing is you can do this in 3D view. So if you add a height onto the hexagons, what we had before in my area, you can now just start to bring this a bit to life with a 2.5D attribute. So you can really start to see how there's some real peaks going on in Manchester and in London. So yeah, that's also really useful. But the problem with a grid is you're stuck at that resolution. So what if we really, really want to keep zooming into London and find out more detail? And again, the hex is kind of stuck at that level. Great for single view and also very useful for regional view. But we have one more trick up our sleeve. So we're going to go to the options again. We're going to duplicate the layer, and this time we're going to create a cluster map. So not to confuse with data science clustering, all this is doing is spatial clusters, putting groups of the data together. So just turn so we're going to change this over to a cluster type map, and this is great because now again you've got your hex counts. And you know, so you've got the counts for that cluster area that you're viewing, but at the same time, as you want to interactively go into Scalar, into the different levels, it's going to give you the more detailed cluster groups and counts interactively, and you get those total points automatically with the tooltip. However, what this is then, just the last thing to show you is the dual view. So we can just turn on the dual view, and wouldn't it be really useful if we could actually look at our point layer as well to actually identify those schools within those clusters rather than just being stuck with the tooltip. So in the legend options, on this side we'll have the cluster map. On this side, actually the first thing to do at this point, I'm just going to save the application because it's always good to save your work in case anything goes wrong. So it's very, very simple. You just export your map to, you can also export the data frame. You can also create some static shots. So if you're just doing a presentation and you just need quickly some images, but most important thing, and you can also share URL. But for the export map, it's literally HTML, and this is where you'll need a Mapbox token. Fortunately, here's one I prepared earlier. So you just put your Mapbox token in there. The other key thing is if it is for maybe a client or someone who's not very savvy with the controls, you may want it read-only, but it's very useful for the user to also have the options of the filtering, and so select the edit, the map option. Then we will export this, and it simply is a download as an HTML file. We're going to open this up, and now we have our own standalone file of all these layers. So now I'm just going to quickly show you the options. So on this side, I think we'll keep our points, and on this side, we're going to keep our cluster. So I'm just going to hide this a bit, and now you can see that you've got both things together. This one's great, you've got the total points automatically, but wait a minute, you've got some really weird tooltip options here. And that's just because it takes the first few columns of your data. So it's very, very simple. You go into your tooltip interaction options. We're going to take off all this status score. That's just to do with some geocoding exercise that was performed prior. And then we can just click and choose what else you want to show. So I think it'd be useful to have the name of the school, and we'll just leave it at that for now. So automatically now, if we're looking at, and the other good thing is everything is being mirrored. So as soon as you zoom in on an area, your other map is reflecting that. So this means now you know that this is a total cluster point, and it's a site of interest. You can pick up on this on the other side, and you can get the name of the school usually. Also, this has also shown that your cluster blobs are actually a bit large. So what we can do is very easily, I didn't fully customize the options. I wanted to show how different ones worked, but it's very simple to change that radius down a bit. Also, there are some other options for coloring. So if you're aware of quantiles, that's very useful because it's that percentage or proportion into the color ramp. You can also do it on size. We'll keep this on quantiles and on the also on the point count. But again, you've got those options to vary things and the radius. So I hope this starts to show how you can easily look all over the country and pan, but not both understand the high-level strategic clusters, but also go into that granularity detail. So I hope that's a useful run-through of all the what you can do with point data. Obviously, you can bring in line data. GeoJSON's the best format for that, and you can use polygons. The reason in my last demo we had the polygon layer, that was just, so we brought the hexes in as a polygon layer. We didn't do that on the fly because of all that pre-processing that I explained earlier has had to go into creating those hexagons. And it's a set grid that the GLA and TFL use. Therefore, on here, as an option, you're bringing it in just as a polygon option. But with points, it's brilliant because you can do on-the-fly binning. There's also all sorts of tips and tricks. You can use arcs are very, very attractive when you've got line data and can look great between like rail station trips as well. And there's all sorts of things there for you to try out at home. So I hope that's been a useful intro to Kepler. I hope that will get you on your way of bringing your data to life. And thank you for joining this webinar.